Topic 7C, multivariable finite difference method. In this lecture, hopefully we are masters at the ordinary one-dimensional finite difference method. And what we want to do now is talk about how to solve problems that have two unknown functions, or 3 or 4, or really any number. We'll work on 2 here, but the extension to 3, 4, any number is straightforward. So pretty much any time we have multiple variables, we're going to adopt what we call a staggered grid. That isn't always the case, but almost always. So we'll talk about multiple variables and how that leads to a staggered grid and why we do that. After that, since we have a staggered grid, that implies that something different is going to happen with our derivative matrices. So we need to talk about that as well. And then we'll tie all of this together with an example. This should be a relatively short video. Forget for a moment that we are working towards a staggered grid. And suppose we're presented two coupled partial differential equations that have two unknown functions, f and g. Since we have two unknown functions, we need two equations, and so we have this coupled set of partial differential equations. How would we solve this? Well, following what we've done before, we would approximate these with finite differences. So we do that. Now my question is, looking at these finite difference approximations, does this work? Is this the best thing that we can do? It turns out this will work. However, we can do better. What's wrong here, if we notice our finite difference approximations, we are actually spanning our grid by a distance of 2 times delta x. We would like to only span 1 delta x. That will make our finite differences more accurate. So while this works, we can do better. So now let's rewrite our finite differences this way. We're writing these finite differences so now we only span 1 delta x. That forces us to say f at x plus delta x minus f at x minus delta x over 2. We're dividing that delta x over 2. But then that we span only 1 delta x. Since we're spanning less distance across our grid, that makes our finite differences more accurate. So the question is this a good formulation? It turns out no, because this forces us to have to know the value f and the value g at the midpoints. We're only storing f and g at integer multiples of delta x, not at those midpoints. So this isn't going to work for us. What should we do next? Let's express our finite differences only at x and x plus delta x and 2 delta x and 3 on. So we write our finite differences this way. Now the question again, does this work? Is this better? We're only spanning 1 delta x. We're only using f and g where we're storing values. Does this work? The answer to this is a little bit more tricky. It turns out this is still not good. If we go back and remember what we were talking about in finite differences and we look at this, where would this finite difference exist? Where would it be calculating the derivative? And it turns out at the midpoint between x and x plus delta x. So while we only need the function f at the integer multiples, that finite difference term exists at the midpoint. However, g doesn't exist at the midpoint. So we're incompatible here. Our terms are not being defined. They're not existing at the same points in space. And so this is not a healthy way to formulate the finite difference method. So we're still not there. Let's think about how we can yet rewrite our finite differences again to try to fix everything. So now look at what is happening. All of our finite differences are only spanning delta x. That's fine. F, we only need at the integer multiples of delta x. But in order to make the left and right-hand side of this equation equivalent and work if the left-hand side exists at delta x over 2. We need the right-hand side to exist at that same midpoint. So we need g at x plus delta x over 2. And it appears that this maybe wouldn't work. However, what if we just defined f to exist at the integer multiples of delta x, and then g at the midpoint between those points? So we are staggering where f and g exist so that we can write our finite differences in a way that only spans one delta x. Let's see what this looks like. So on the bottom, I'm drawing our grid. And if we look from blue point to blue point, that is spanning one delta x. We would call this one unit cell on our grid. So we will place f at the integer multiples of delta x, and we place g at the midpoint. If we do that, the finite difference equations that we wrote up top work just fine. And our finite differences only span one delta x. But we need to keep in mind that the values we obtain for f and g exist at physically different points. We don't want to confuse that. If we're simulating waves, the wave for f and g, even though they're in the same unit cell, might have the same array index. They exist at physically different places and will be out of phase. Could have a slightly different amplitude. So we need to keep that in mind. Now, just for your interest, when we solve three-dimensional problems, we still stagger things. What we're looking at here is not something we will need in this course, but it's called the Yee cell. And it's something that is used all the time in finite difference time domain and finite difference frequency domain. And here we're solving an electromagnetic problem where we have two quantities, an electric field E and a magnetic field H. And each of those are also vectors. So they have X, Y, and Z components. So even though X, Y, and Z are part of the same vector, when we look at how the finite differences are written, we end up staggering these. And that makes the finite differences work, but it's a little bit strange in how we reconcile, because our different components of our same vector are in physically different spots, could be inside different materials. The wave at those points could have slightly different amplitude. It will be out of phase. And we need to keep this in mind. But this is a good example of what staggering looks like in 3 dimensions. Now, we've been writing our finite differences in terms of x and delta x. What is more useful for solving a finite difference problem is writing it in terms of the array indices. And in this case, the array index will be I. So I've rewritten our finite difference equations, but rather than using x and delta x, using the array index I. Now, one thing sort of tricky that we need to keep in mind, for example, we have an f sub I and a g sub I. Even though they have the same array index, they're staggered by a half cell, and they're in physically different locations. We need to keep that in mind. However, the array indices make our derivative matrices and stuff like that more straightforward to formulate. So I will write the finite difference in this form as opposed to what we showed on the previous slide with x and delta x. So now we understand when we have multiple variables that we need to stagger the grid. This is to have healthier and more accurate finite differences. This affects how we write the derivative matrices on a staggered grid. So let's take a look at this. We have on the left our first differential equation written in finite difference form and array indices. And so what we will do is we will look for every point on our grid, every cell on our grid, we will write that finite difference equation once. So here we have 5 points on our grid. So we write this finite difference equation 1, 2, 3, 4, 5 different times. Now our finite difference equation contains an I plus 1 term. That means at the very last point, that finite difference equation wants F6, which of course isn't stored, and we need to do something about it. And that's called a boundary condition. No surprise there. Now we write our second finite difference equation. Notice this finite difference equation contains an I minus 1. That means the first equation will contain a G naught, or G sub 0, which doesn't exist. And so we need to fix this, and that's called a boundary condition as well. Now notice on the last slide that the two different differential equations had their boundary conditions at opposite sides of the grid. And this is why we're going to need different derivative matrices, whether we're doing derivatives on F or derivatives on G, because of the staggering and the boundary conditions. It forces those matrices to be slightly different. We'll find out they're related, but they can be slightly different. So right now we have our 5 equations, and we can put these into matrix form. And so on the right, we have our column vector of our G's, which are not known yet, this constant A. We have our column vector of F's, which is not known yet. And we can take a look at our finite difference equations and write that this will be our derivative matrix. Notice the position. It's not a symmetric matrix anymore. It has negative ones going down the center diagonal, positive ones in that +1 diagonal, but zeros in that lower diagonal. All of the derivative matrices we've been writing so far had symmetric matrices. This is no longer symmetric, and this is due to the staggering. Also notice for that last equation, we used Dirichlet boundary conditions because that's the easiest. So what came out of this is our derivative matrix that we'll call D with a superscript F. That will remind us that that is a derivative matrix to take derivatives of F, not G. We would not want to apply that to G. And so out of this analysis came that derivative matrix. Let's look at the other differential equation, or the other finite difference equation. And we write that finite difference equation once for each point, and then put this into matrix form. So we have our column vector of F's on the right, our constant B, and on the left we have our column vector of G's. And if we look at our finite difference equations, we can figure out this is the square matrix that would calculate a derivative on G. And that becomes our derivative matrix, which we'll write with a G superscript to remind us that that derivative matrix is taking a derivative of G. Now let's look at the symmetry of it. It has ones going down the center diagonal, negative ones going down the lower diagonal, and zeros on the upper diagonal. This is different than the previous derivative matrix, so these are not the same. And by the way, for that first equation, we use Dirichlet boundary conditions. So our derivative matrices are different depending whether we're taking a derivative of F or a derivative of G. And that's very important to realize. When we stagger our grid, the finite differences change. So this is all we've done so far. We've gone from our 2 analytical coupled partial differential equations to 2 matrix equations. And we realize that those derivative matrices are different. Now, if we practice this, what we've written here is the only step we need to do on paper. We really don't ever have to explicitly touch finite differences. So we went through more detail so you could understand what's happening when there's multiple variables and that those derivative matrices are actually a little bit different. Now at this point, we want to think about solving this system of matrix equations. And there's really 2 approaches that we could take. So we have 2 equations, 2 unknowns. We could actually write a large block matrix, a 2 by 2 block matrix, and solve this simultaneously. This works, and for small problems, it works just fine. However, this 2 by 2 block matrix is bigger than it needs to be. We'd rather just write it with the same size matrices as the derivative matrices. So to do that, we would take one of our matrix equations and substitute it into the other to come up with a single matrix equation. So what I've shown here is I solved this first equation for G, plug that expression in for G in the second equation, and then I have a matrix equation only with F. And here's the original equation that I had solved for G. So what we can do is solve this first matrix equation for F, and once we have an answer, just immediately calculate G from it. This is a bit more numerically efficient, so this really is the preferred way, but maybe there's something happening with what you're doing that requires you to solve them simultaneously as a block matrix, and that's fine. I just want you to see both approaches. We will take the approach on the right. Now, let's look at this equation, and I want to point out something very interesting happened. Notice we are multiplying our two derivative matrices together. Really, this is a second order derivative matrix. But remember when we talked about this last time? We took our two first order derivative matrices, multiplied them together, and got something that didn't work so well because we're spanning too far out into our grid. So we had to build a whole separate second order derivative matrix that expressed our finite difference a little bit tighter on the grid. That improved the accuracy. But that's what happened before. Let's look at what happens now because we're multiplying two derivative matrices that look slightly different. So when we do this, when we multiply these together, look at what we get. This is exactly what we wanted for a second order derivative matrix. That works perfectly. So once we've staggered our grid, we can multiply these first order derivative matrices together and get a very good second order derivative matrix. So that's very cool. And that saves us a lot of work when we're formulating. Now we look at our two derivative matrices. We see that they're not symmetric, and we see that they're kind of transverses of each other. It turns out they are related, and they're related through a, first we take the transpose, then take the complex conjugate, and then bring a negative sign into the matrix. So it's the negative Hermitian transpose. That's how they're related. So why the Hermitian transpose? Well, it's not something we've talked about yet, but when we start doing simulations with complex numbers, we'll need the Hermitian transpose there. But for now, we can just think of it being a transpose. And as long as all the numbers are real, the ordinary transpose will work. And why the negative sign? Well, that's because, let's look at this first matrix. If we take a transpose of it, we will still have negative ones going down the diagonal. We'll just have positive ones in this diagonal and zeros up here. Well, the other matrix is the negative of that. So that's why we need the negative sign here. Now, I know from personal experience this works anytime I incorporate Dirichlet boundary conditions into my matrices, periodic boundary conditions, something else we haven't talked about, and I don't think we will in this course, Floquet boundary conditions, and there's probably lots more. This relation works. Other boundary conditions we talked about, the Newman boundary condition, I know that this does not work for that. And there may be other exceptions where this doesn't work. So test it, try it. If you have a new boundary condition, make sure that it does work. But I can certainly confirm for Dirichlet, periodic, and Floquet. So what this means, when it comes time to build the derivative matrices, assuming we're not using a Newman boundary condition, this means we only really have to build one. We can construct the other just from the negative Hermitian of the first one. So it halves the amount of work we have to do to build those derivative matrices. Some final notes and things I want to talk about. After doing this a lot, there's really two approaches. We can start with our set of partial differential equations and convert immediately to matrix form, and then start doing matrix algebra to combine equations until we finally get the equation that we want to solve. Or we could stay analytical, combine our equations until we get this final equation, and then bring that to matrix form. In my experience, that's more work to do to manipulate the equations analytically. And a lot of the times the fixes that we'll put in to fix some numerical issues, they're easier to fix in the very beginning. So you will see me take the initial set of coupled partial differential equations and convert to matrix form very, very early in the process, and then formulate the final equation I want to solve with everything in matrix form. The other thing when we convert early in the process is that usually we only ever need the first order derivative matrices. Not that I've simulated everything out there, but I've never had to develop a higher order matrix than just first order when I'm doing these staggered grids. So another benefit of jumping immediately to matrix form in the very beginning. Also use the fact that the derivative matrices are related through the negative Hermitian transpose, so that halves our work when it comes time to build these things. Another really cool thing that happens, if you were to formulate this analytically, sometimes you'll end up with a derivative of a derivative, but there's another function in there. And then you end up having to use the product rule, and you get a lot of terms, and things become rather tedious. But if you're doing this in terms of matrices, you would just write it this way and everything works itself out. So we don't have to use the product rule on here or think about it too much. And some really magical stuff happens when we have an expression like this, and it simplifies what we have to do. Okay, let's do an example. We are actually going to solve a real set of differential equations and take this all the way through. So let's say we have these two coupled differential equations, and we want to solve it in the interval of 1 to 10. And we also have some boundary conditions here. We know the value of f at either end of the bounds. So we have enough information to solve this, and we want to find both f and g. The first step, and we can do this on paper, but it's an immediate step, we jump from the analytical equations to matrix form. And we're doing the same thing we've always done. We've gone term by term. Just now we recognize we need a staggered grid, so we have different derivative matrices operating on f and g. We would not want to write those as the same derivative matrix. So we already have the matrix form of what we want to solve. Step 2. I want to put the final equation all in terms of f. Why am I choosing f? Because the boundary values that we were given in terms of f. So I want my final equation to be terms of f. That means right now I want to take that first matrix equation and solve it for g. Once I have that, I can now grab the second equation and replace g with the matrix equation that I just derived. So I'm essentially combining the first and second matrix equations. And I simplify and I end up here. And I have my final matrix equation all in terms of f. At this point, I want to put my matrix equation into standard form. In this case, it's AF equals 0. And I see that my A matrix is the derivative matrix operating on G times the derivative matrix operating on F plus 2 times the identity matrix. Okay, now we're moving to MATLAB. Everything we've done there is something we would do on paper, and with practice is very simple and quick to do. So in MATLAB, we want to set up our problem. So I'll initialize MATLAB, close all the figure windows, clear the command window, clear memory, open a figure window with a white background so that we can plot the answer into. And then we want to define everything about our problem. So we have our bounds, xa and xb. We're solving this in an interval 0 to 10. And then we have fa and fb. Those are our boundary values. That's what the function is at points 0 and 10. And I'm choosing to use 1,000 points here. So that works here. But really what we'd want to do is probably choose 20 points. Solve the problem. Pick 40 points. Solve the problem. Does our answer change much? And keep cranking up the number of points until the answer doesn't change much anymore, and that would be convergence. This is such a small problem, I cranked up the number of points just so we got a nice answer, and it really doesn't affect the speed too much. But this is a little bit sloppy and lazy, and when we get to bigger problems, habits like this would hurt us. But not really a big deal right now. Okay, so now we're in the actual work, and the first thing we want to do is calculate our grid. So I calculate the grid spacing, and then I calculate an array that tells me the position of each point in the interval from XA to XB. Now I want to build my derivative matrices. So what I'll do is I'll build a derivative matrix that operates on F, and then I don't have to do that again for the derivative matrix that operates on G. I'll just calculate the derivative matrix for G immediately from the derivative matrix of F. Okay, so how do I build the derivative matrix of F? Well, first I'll declare it a sparse matrix. Then I'll add the diagonal along the center that has all negative ones. And then the upper diagonal, the diagonal number 1, I put all positive ones, and then I divide it all by dx. So I've built my dfx derivative matrix, and then my dgx derivative matrix. I'm now ready to build the matrix equation. So that's step 4. And when I calculate A, this is an equation. I feel like I'm just typing in the differential equation, but the derivative matrix for G times the derivative matrix for X plus 2 times I. So I had to build that identity matrix, and so I created a sparse identity matrix. We now have our matrix equation, but it's not yet solvable because we have to build in our boundary values. In fact, at the boundaries, we've built Dirichlet boundary conditions into those derivative matrices, so things would go wrong at the boundaries. But that's not a problem because we're throwing out the information at the boundaries and building in our boundary values, just like we did before when we were solving ordinary one-dimensional finite difference equations. So remember what we did. We zeroed out the rows. We threw out the finite difference equations at the boundary points, put a 1 in the diagonal position, and then over in the last column vector for our excitation, that's where we put our boundary values. And so that's exactly what we're doing here, and it's no different than what we did before. Step 6 is to solve the matrix equation using backward division. And so we solve for F. And then from that, we can calculate G. During our formulation, this was the very first equation that we derived by solving that first differential equation or matrix equation for G. So we've now solved our problem. The only thing really left to do is to plot the answer. So here's the code for plotting. And when we do that, here's what I get for the answer. So we see our F and we see our G, and it looks like cosines and sines with slightly different phase. And that's all there is to doing a one-dimensional finite difference method involving multiple variables. If we had, or multiple unknowns, if we had 3, 4 unknowns, we would have 3, 4 matrix equations, and we would just combine them until finally we had one matrix equation that we could solve. Or we could choose to build one big block matrix and solve it. Either way is fine. My preference is to whittle it down to the smallest matrix equation possible. So that's it for multivariable finite difference method.